Okay, so welcome to the sixth problem solving session for this course. Today we'll be solving assignment 6 for this course, and the problem is as follows. Which of the following assumptions is made in tight binding model for energy band calculation? Now, the first thing in tight binding model is that the first one of the assumption in tight binding model is that electrons are bound tightly to the nuclei, and when electrons are bound tightly to the nuclei, the orbital functions become atomic like. They have atomic wave functions, and therefore the correct option is that electronic wave functions are plane wave like. Electronic the kinetic energy is low. The electron wave functions are atomic like. So correct option is option 3. Now electronic kinetic energy is low. This thing we cannot say because when the electrons are bound tightly to the nuclei, they move very fast, and therefore electronic kinetic energies are not low. Okay, and potential due to the core ions cannot be ignored. This statement is false. And electrons move in the potential of local atoms, but electrons always move in the potential of many atoms. Now the second question is that the energy bandwidth calculated from tight binding method is. Now if one writes the energy band dispersion relation for calculated from tight binding model, one finds Rn, where this term is the transfer integral. So we can say that energy is proportional to the transfer integral. Proportional to the square? No, proportional to the transfer integral. The other options are not correct. Now moving on to question number 3. The energy dispersion relation in an energy band is given as this is the relation given to us. The width of the energy band is. Now in general, when one talks about dispersions, one usually is talking about, let's say I draw a function which goes like this way. So dispersion in, let's say if I say this is f of x and x. So dispersion relation in this case would be the range of values a function can take considering the variables from minus infinity to plus infinity. So in this case the function can oscillate between this value. So the dispersion, let's say if I say the value of f of 0 and this is whatever the value, let's say if I'm able to, if I write this point f of 0 as b, and if I write this as a is equal to f of 0, or this is a bit puzzling. Let me just clear it. I'll clarify it again. The function goes from going from here to here. The function has maxima at this point and minima at this point. So the range of values are these. Now in the similar way, and if I say that this is a cosine function, then the cosine oscillates between -1 and 1. So the dispersion between cosine values would be 2, because cosine can take -1 value and +1 value, so total dispersion would be 2. Now in this case, ek is equal to minus of alpha minus 2 beta cosine kxa plus cos kya plus cos kza. Similarly, in this relation also we can say that the minimum value, this ek can take, will be when cosine of k kx is minus 1, cosine of kya is minus 1, and cosine of kza is minus 1, and therefore and maximum of E of k would be when cosine is plus 1, and plus 1, right? So if minus 1, minus 1, and minus 1, if you add them, it becomes minus of 3, which one comes out in the out of the bracket becomes plus of 6 beta, minus of plus of 6 beta, and the maximum value this it can take is plus of 3, which comes out as minus of 6 beta. So the function E of k, if or in specific, I can write E of k plus alpha, and in the case of minimum, and E of k plus alpha in the case of maximum. This becomes plus of, or I should say, because it's a negative sign, I should replace this as max and this as minimum. Similarly here at max and this is minimum. So maximum would be 6 of beta, because minus 3, this thing and this thing come out, become 6, and this becomes 6. So the dispersion between these two 6 beta would be 12 beta, and therefore the width of the energy band, that is the dispersion we have, is 12 beta. Now the fourth question says that the nearest neighbor atoms on a simple cubic lattice has the transfer integral J. So we have to find its contribution to energy dispersion. Now, as we have noted above, E of k is given by summation n transfer integral magnitude of the lattice translation vector multiplied by E of minus k dot r of n. Now in case of nearest neighbor, let me draw a cubic lattice and then we can easily find it out. So this is a simple cubic lattice, and let us say I am considering an atom at this position, and let me denote it as 0, 0, 0, and these directions, let's say this is x, y, and z direction. So if I take another color, if I draw the other neighbors, what I find is neighbor 1, 2 at position, these positions. Let's say this has 3, this one 4, above 5, and down as 6. And also let me write the coordinates of these neighbors. Now 1 in the y-axis is behind the origin, so I would write this as 0, 2 would become 0, 1, 0, 3 would be 1, 0, 0, 6 would be 0, 0, minus 1, 5, 0, 0, 1, and 4 is behind the x-axis, and therefore will be minus 1, 0, and 0. Now since we know all these neighbors, now let me take an additional page. So let us write ek. So first I will write all the vectors, all the neighbors. Okay, and we can create vectors from this 1, 0, 0. Let's say if I take this example, then Rn in this case would be I mean, in this we are not provided with the lattice, so but seeing the options, we can say that lattice constant is given to us as a. Therefore I can write a I cap plus 0 j cap plus 0 k cap, and in other cases I can write it as 0 I cap plus a j cap plus 0 k cap, and the other is 0 I cap plus 0 j cap plus a k cap. So this is the way by which we can write these lattice translation vectors. And also we can write k vectors in this case as kx component I cap plus 0 j cap plus 0 k cap, here 0 I cap plus ky j cap plus kz 0 k cap, and here 0 I 0 j plus kz k cap. Now let us evaluate, now put all these values in this relation here. Okay, and j of Rn in this case would be, since Rn we are talking about nearest neighbors and all those neighbors are placed by distance a, so it becomes j of a. So ek, j of a is a constant quantity, comes outside, and we have a summation which runs over all the exponents. Now the first I, which k dot r, this, if I talk about this one, will become ai cap, or in fact k dot r becomes kx I cap plus 0 j cap plus 0 k cap dot ai cap plus 0 j cap plus 0 k cap. So if in this relation I dot I becomes 1, kx and a only the first term survives and the rest of the terms cancel out. So I can erase in this exponent, I can erase rest of the terms and only keep the first two terms. In the same way, if I go further, I can find minus of I. There will, now since we have 1 0 0, there also exists minus 1 0 0, and in that case I would have minus of kxa. Similarly for ky component, I would have minus of I minus kya, and for the z component we will be having in this way. Okay, so let us collect the terms. E to the power minus I theta and e to the power plus I theta, if divided by 2, becomes 2 cos kxa. The next two terms collected together becomes 2 cos kya, and next is 2 cos kza. 2 comes out of the bracket, cos kxa plus cos kya plus cos kza. So this is our energy dispersion relation in tight binding model for nearest neighbor interaction, and therefore the correct option would be 2j cos kxa kya kza. Now if we do the same exercise with the second nearest neighbor sites in question 5, to understand the second nearest neighbor site, let me just show you by drawing the second nearest neighbors. So in this figure again, I can write the coordinates as 0 0 0. Let me take another. So second nearest neighbor in this case would be the atoms situated face diagonally apart from this 0 0 origin, whatever let me call it as point A. So if you go in this direction, this point is separated by root 2a if the distance is a, and similarly in this direction there will be another point. And if I'm talking about this plane, the horizontal plane, okay, there will be another atom in this position and there will be another in this position. So if I just like the previous problem, if I say that this is, let me take a different color. If I say that this axis is x-axis, this is y-axis, and this is z. So if you keep yourself in the xy plane, okay, in the xy plane, there are 4 neighbors. Similarly, in the YZ plane, which is the vertical plane in this case, we can find, I will take some other color. So this point, if I join this, there will be a vertical atom here and another here and another one here. In the same way, YZ plane will have 4 neighbors, and ZX plane, if I draw it, it will become much more complicated. It will, one can imagine it will also have 4 neighbors. So total we have 12 second nearest neighbors, and let us let me write down the relation ek. Now, and these 12 nearest neighbors, we can write it as follows. Let's say if I am in the xy plane, and if I am talking about +1, +1 and 0, so +1, +1, 0 would be this one, which is in the positive half of x and y. -1, -1, 0 would be the opposite one to this thing, this point, and we have -1, -1, 0. We can also write other 2 variants, I'm not seeing on the diagram, and in this way we can write for the xz plane +2, these are the 2, and we can write other variants as this, and in the yz we can write them as follows. So these are the RNs we have for the second nearest neighbors. And similarly, we can also imagine the k vector to be composed of kx I cap, ky j cap plus kz k cap, and k dot r of these I would write directly in the ek diagram. Since j this time is the second nearest, so Rn is √2a, and the first k dot r is for this vector, which comes to be kx a plus ky a. Second one is for this one, minus I minus of kx a minus of ky a. Third will be for this one, plus minus of kx a minus ky a, and the last one is plus e to the power minus of kx a plus ky a. And also we can write down as follows for the rest of these 4 and these 4. I will give you an analogy by solving the first set, and similarly we can write for these second and third. Now if I restrict with the first, I mean, of course there is a plus sign which goes for the second set and for the third set, but right now we will consider the terms 1, 2, 3 and 4, and then similarly we can treat the second set and third set. So j of root 2a becomes, I can write it down as this. Now if I take e to the power minus kxa as common, then remaining in this bracket is e to the power minus I kya, and if I take one more e to the power minus I kxa from this and then join this here, it becomes e to the power minus I minus kya, and from the other two terms that are missing, if I take out again e raised to the power plus I, in fact here at this time I'm left with e to the power minus I minus kya plus e to, now in this term, e to the power minus I kya. It solves to e to the power minus. Now these two terms are same, so I can take out these as common, e to the power plus I kya common, and we have another factor coming up, e to the power I kxa plus e to the power plus I kxa, and of course we have j times root 2a in the front. So this term multiplied by divided by 2 and this term divided by 2 counts to cos theta, so it becomes 2 cos kya and multiplied by 2 cos kxa, which simplifies to j root 2a in the front, and the first 4 sets simplifies to cos of 4 cos kya cos kxa. And similarly, now the second set and the third set I can write here as 4 cos the other two factors, that is kya cos kza plus 4 cos kza cos kxa. Okay, and let me take a separate page, and 4 is a common factor coming out of this big bracket. 4 times j root 2a, we have 3 factors, xy cos kxa cos kya. Similarly, now this is xy, we will have yz and zx. So this will become the energy dispersion relation for the second nearest neighbor, and correct option would be 4 times j. Now since the thing mentioned is transfer integral as j, so j of root 2a can be treated as j in this case. 4 times j, xy first component, yz second component, and zx third component. So correct option would be C. Let's go for the next question. Next question wants the energy dispersion relation for the third nearest neighbor sites. Now to understand this time again, let me very quickly draw a simple cubic that is for you. Again I am taking 0 0 0. Now third nearest neighbor in this lattice would be an atom sitting on a body diagonal across 0 0 0. Let me draw it with a different color. This atom is separated root 3a distance, and if I think of these as the 3 axis, it is sitting in an octant. Okay, this whole cube is a part of one octant. I can draw a similar cube at this position would be a second one, third would be below this, fourth below this, and then other 4 will be in this plane towards me, towards out of the paper. So there will be 8 octants. One octant, that is drawn in the red color, contains one body diagonal which is across 0 0 0, atom across 0 0, and other body diagonal which I have shown will be this one, and another one will be down here, and this 4 things will come out of the paper. There will be another 4. So one octant has one body diagonal which is 0 0 0, and 8 octants will have 8 body diagonals, and 8 body diagonals means 8 nearest neighbors, or I should say 8 third nearest neighbors. So if I draw, let's say 1 1 1 is the point. Now if I take this as the plus x and this as the plus y, so this will be plus z. 1 1 1 would be a point which would be this point, which is body diagonal from here. Okay, we can draw variations for 1 1 1. We can do the permutations, 1 1 minus 1 1 minus 1 1 minus 1 minus 1 minus 1 plus, sorry, minus 1 1 1. These are the thing, and we have minus 1 minus 1 minus 1. So these are the 8 combinations of these 8 nearest neighbors we can draw. Fine. Alright, and similarly we can write the EK as, now this time j would be root 3 times a, e raised to the first power. Now minus I for the first 1 1 1, I can write kxa, kya, kza. Then for the second one I can write minus I kxa plus kya plus kza. Oh, that would be minus here. Then plus e raised to the power. Now 2 we have taken care of. I am writing here for third. Minus I kxa minus kya plus kza plus e raised to the power minus of kxa plus kya plus kza. Other 4 terms to the power minus I minus kxa minus kya minus kza plus minus kxa minus kya plus, sorry, I should be outside. Let me write I is outside, minus kxa minus kya plus kza. Rest of the 2 terms e to the power minus I minus kxa plus kya minus kza plus e raised to the power minus I kxa plus or minus kya minus kza. Now these 4 terms, out of these 4 terms, let me, so this j root 3 stays outside. Let me take e to the power minus I kxa common. Now I kxa common taken out from this term leaves me inside e to the power minus minus I kya plus kza. Then taken from the second term leaves minus I kya minus kza. From third term leaves minus I minus of kya plus of kza. And I am taking from this term e to the power minus I kx common. It would be minus I minus of kya minus of kza. Now I'm closing the small first bracket, so these are the two brackets I'm talking about. Okay, then I can take out e to the power I kxa common. From this term I will be having, there's an I here, I will be having e to the power minus I kya plus kza. Then from this term minus of kya minus of kza. Then here power minus I minus of kya plus kza plus e to the power minus I from last term minus of kya minus kz. And here I close the two brackets. So now if you note carefully, this bigger bracket and these two brackets are in fact equal, because you can see first term is here, the last term is here, ky minus kz term, ky minus kz term is here, and k minus of ky plus kz is here. So what I can write is these two big terms minus of ei ky a plus kza plus e to the power minus I minus of kya kza plus e to the power minus I minus ky plus, and we have the last term. Let me take a page. Out of we have e to the power minus I kxa plus e to the power I kxa. So now in the first two, this first bracket, let me simplify it down. It counts to, if I take e to the power minus I kya common from this bracket, I get inside e to the power minus I kza. And if I take e to minus kya from this one, I have minus of minus kza plus e to the power, this time take I kya common from this bracket, we get minus of minus kza plus the rest of term available to us is kza. And of course we have this term here, and we have this big bracket. Yeah. So now we are left with three factors, because this factor and this factor is same. I kza plus minus minus plus, so plus kza. We have minus I kya and e to the power minus I kza plus e to the power I kza, and in front there is a factor common running. So divide by 2, divide by 2 and divide by 2, or I say multiplied by 8, gives me 8 times j cos 3 j root 3a. This term becomes if I write the, sorry, this is x here, if I write like this, cos kxa, cos kya and cos This is the energy dispersion for the third nearest neighbor in tide bonding model. 8 times the transfer integral and multiply of 3 factors. So we have 8 times j, kxa, ky, kza. Okay. Now question number 7, which says that energy dispersion relation considering up to. So we are considering first, second and third, all 3 nearest neighbors of a simple cubic lattice. Now this time lattice constant is mentioned along the gamma x symmetry line is given by, now there's a information provided 1 less than mu less than 1. So let us write the 3 dispersion relations that we have derived in above 3 questions together. E k is nothing but E naught plus the k, which is nothing but the crystal field integral. Then we have, now for the first j we had in first nearest neighbor. If we go above, this was the question. So the relation is 2j summation of 3 cosines I'll quickly go there. So we have 2j and summation of cos kxa plus cos kya plus cos kza. Then we had the second nearest neighbor relation, which was 4 times j and summation of 3 factors. 4 times j cos kxa cos kya plus cos kya cos kza cos kza cos kxa. This is the second. And the third, which we have just derived, is 8 times j multiplication of cos kxa cos kya and cos kza. Now the information given to us at this point is, take a separate page, is the gamma x point. Now since we know from our previous assignment solutions that x point is the point pi by a 0 and 0 in 3 dimensions. Now in this question the information 0 mu 1 given to us is, now if this were the x component then it becomes kx, ky is 0 and kz is also 0, but mu is, there is a information 0 less than mu less than 1. So most likely the mu turns these values into fractional coordinates. So lattice constant, which was from 0 to a, now becomes so mu turns, let's say I have pi by a, the k, and if I multiply it by, let's say, mu times a, which is the fractional coordinate, mu is less than 1, and if I say this becomes this quantity, so actually ax becomes mu times pi. In the same argument, ky is 0 times mu a, still remains 0, and kz is 0 times mu a, it still remains 0. So if we plug in kx as mu pi and ky as 0, kz as 0 in the above relation here, what we get is as follows. Okay. mu pi by a. Let me just take a second here. Cos of kx in a okay. So there is a bit modification here. I would write this as kx times a in this sense. Now since this information transforms this into fractional coordinates, so kx into a in some sense becomes pi by a times mu a. Okay, the whole kx into a, in fact I should write, becomes mu pi. Okay, because kx is this part. So if you plug in kxa as mu pi in the above relations and ky is 0 and 0, what we find is as follows: ek e naught plus 2j. Now this j is the first nearest neighbor, so I will write a, and in first bracket kxa becomes cos mu pi. Then other kya is 0, so I will write cos 0 as 1 plus another factor cos 0 as 1 plus 4 times j. Now first cos kxa and cos kya, I would get only cos mu pi. Then we have cos kya and cos kza, so this counts to 1. Then cos kz and cos kxa is mu pi, so I will again as cos mu pi from the second bracket. And this, since this j works for the second nearest neighbor, I would write this as 4 times j root 2a. Then we have 8 times j, which works on the second nearest neighbor, and we only have cos kxa which survives, so cos mu pi, rest of our 1. So if you simplify this bracket becomes 2 plus cos mu pi multiplied by 2j of a. Then second bracket simplifies to 1 plus 2 cos mu pi, and third we have 8 times j for the second nearest neighbor is cos mu pi added with e naught plus k. And this relation is second. Here we have e naught 2j this. Now question number 8 is for the according to Slater-Coster rule, if we consider 4s, 4p and 3d orbitals of a cubic lattice, how many unique sigma overlap integral can be possible? Now unique sigma overlap from s, p and d are, first we can talk of ss overlap, sigma overlap. Sp can be there. Sd we can talk about. Sd, let's say we have a spherical orbital and a dz square orbital. This is one of the example. S can be, one can have whatever. This is say pz, or I can say dz square. S and s can be 1s and 1s. Then we have pp overlap. This is pp. Then we have pd overlap. This is pz, let's say this is pz. If I'm talking about pz overlapping with dz square orbital, then also I can have dd overlap for 2 dz square orbitals. Now these are the three or how many, 3 and 3, 6 unique sigma overlap integral possible with 4s, 4p and 3d. So we have 6 unique. The rest of those are would be nothing but repetitions of these. Ninth question is, according to Slater-Coster rule, if we consider 4s 4p and 3d orbitals of a cubic lattice, how many nodal planes are there in the integral Vp pi r? Now if one considers of pi type interactions of 2p orbitals, let's say I draw pi type interaction. This is one pz pz. So the internuclear axis is this one. So there exists a plane. This plane does not have any electron density, and it also passes through the and also contains internuclear axis. So we call it a nodal plane. And we cannot find any other plane which contains internuclear axis. Now if one talks about a plane, let's say this vertical plane, this plane also does not have any orbital, but it also doesn't have any internuclear axis as a part of it, so this plane is not considered. So only we have one nodal plane for pp pi interactions. So the answer is 1. So this was the missing point which I have already written in the to complete the question. So in the plane wave representation, the size of the Hamiltonian matrix of n-side system with 100 reciprocal lattice translation vectors for each k value in the Brillouin zone is. Now the size of Hamiltonian matrix depends upon the reciprocal translation vectors we have, because Hamiltonian this size we talk about the matrix element with the power just find out. Minus I k plus capital K, and here we have plus I k plus capital K. Now this matrix element, the number of k vectors we have is the size of the matrix element, which would act as a diagonal. So 100 reciprocal lattice vectors would contain 100 columns and 100 rows, and size would be 100 cross 100. Therefore we have 100 cross 100 as our correct option. Now moving on to 11th. For similar convergence in plane wave method of energy band calculation, the number of plane wave required. Now in this particular thing, now for the convergence of these plane wave energy band methods, we require, this convergence is smaller for core states and larger for valence states. This is a particular the result that we have in plane wave energy band calculation. So sort of one has to remember this thing, right? So we have smaller convergence for core states and larger for valence state. The number of plane wave requires is smaller for core states and larger for valence states. Now in this particular question it is a bit difficult to provide an argument, but I cannot provide more information right now, so we have to stay with this particular scenario right now. Now question number 12 is for the convergence in plane wave energy band calculations is best in the case. Now for lower lower levels of bands, and this convergence method behaves or turns out to be very effective. So the lowest band in the given options to us is 1s band. So plane wave energy band calculation is best only for 1s. Now if we go to higher bands, we require more orbitals per site into consideration, which demands more computational time. So it only works for 1s band in the best case. Now in the following question, which of the following statements explains why nearly free electron model is successful? Now the thing is that the valence orbitals are well spread out. Larger kinetic energy of valence orbital near the nucleus cancels the attractive potential to the nucleus. Electron repulsions cancel electron nuclear attraction. Now the thing that to know here is that it is because the valence electrons, when go near to the nucleus, let's say this is the nucleus and we have electrons, so let's say this is the innermost, then second, then we have third shell, and fourth and fifth. These electrons also spend some time near to the nucleus, but when these come near to the nucleus, they have more kinetic energy, because let's say if I'm talking about an electron, let's say 4s electron, and if I draw the radial part of the wave function with respect to the distance it spends from the nucleus. Now 2s starts from above, so 4s s starts from above, so this is for 1, for 2s, for 3s, and this goes as 4. So 4s has 1, 2 and 3 radial nodes, right? And whenever there is a node, we know that it contains a large kinetic energy region, because kinetic energy is second derivative, and whenever there is a node, the wave function changes sign rapidly, and first derivative would be large, and therefore the second derivative also. So whenever there are nodes present, we have large kinetic energy. And let's say in the case of this 4s electron, which spends time near the nucleus, I can also write this 4s as the probability. Now probability will turn everything positive. We have large probability of the 4s electron near to the nucleus, because this is the nucleus, and if we go, so any electron, any outer shell electron spending more time near the nucleus will have large kinetic energy, and this large kinetic energy helps it not to fall into the nucleus, or it cancels out the large attractive potential to the nucleus. So in this scenario, what do we have is the larger kinetic energy of the valence orbital near the nucleus, which it has, cancels the large attractive potential of the nucleus. This is the reason. This is the reason of cancelling, not the electron repulsions or valence electron spend very little time. This is a false statement. And kinetic energy of core electrons cancels the attraction between valence and nucleus. So no, it's not the thing. So the correct option in this scenario is B. Okay. So this way we have completed the assignment 6. Fine. So are there anything that I can explain? One can unmute.
थैंक यू सर, आपने 6 और 7 का बहुत ही मुझे मतलब आई वाज वेरी मच प्लीज्ड फॉर द सॉल्यूशन ऑफ 6 and 7th क्वेश्चन.
6th and 7th. Okay.
हाँ, आई ट्राइड, बट वो ये तो सिंपल है पर थोड़ा सा लॉन्ग है. सर मुझे ये वो फर्स्ट 3 वाले सॉल्यूशन मिल जाए तो मैं आपका आभारी रहूंगा.
First
assignment number 1, 2, 3.
Okay. Actually I can provide you the link. If you go to the assignment, I mean an NPTEL page where these solutions are provided, there will be a page of problem solving sessions, and from there you can find, because as a part of this regular TA sessions that I'm doing, I am also uploading these live sessions, and right now I am screen recording this particular session. So I am posting these sessions on my channel. I can give you the link, or you can also find the link from there also.
Where in the course? Hello?
In the course. Okay, ओके आई स्विच टू हिंदी. जब आप उसके अंदर असाइनमेंट सॉल्व करने के लिए मेन पेज पे जाते हो स्वयं पोर्टल में, राइट, देन इफ सो ऑन दैट स्वयं पोर्टल you will find a page where you will see, if I switch the screen, you can follow the screen, right? Are you able to follow the screen on the... No, okay, sorry, I have shared the screen from other device, you won't be able to do that. Okay sir, what I can do to help you is you can send me your email ID, or you can
ag.rathod@gmail.com.
just please type it in the chat box, I'll see. Type your email ID in the chat box, I'll click a picture of that and would send you the link where I have solved the first 3, or in fact first all the 6 assignment solutions as well as the videos. Okay, just fine, I've taken the picture, I'll send you one email regarding this link.
Okay, thank you sir.
Yeah, sure, fine. So I'll close this present session for now. Thank you, you can log out.
Okay, thank you, good night sir.
Thank you.